Hello, everyone. This is our lesson for the standard normal curve. For this lesson, you're going to need this standard normal probabilities table. I should have given you one. It's purple and laminated. Before we get into this, I want to let you guys know that this is something finding probabilities or areas on a standard normal curve is something that we see again in chapter 7, chapter 8, and chapter 9, I believe. So this process that we're going to learn today is very important. I'm hesitating to say that because I tell you everything in this class is very important, but this is an idea that we see again and that we use a lot in hypothesis testing and sampling distributions and so on. This is also related to that idea that we talked about at the very beginning of the year when I was asking you, does it seem reasonable that this claim is true? Does it seem reasonable that this Ford Focus really gets 41 miles per gallon? We could have calculated that using a standard normal curve. So before we get in, I just want to let you know that this is one of our more important topics because we see it again in different concepts or chapters or units that we're going to do this year. I personally really love the standard normal curve. It's one of my favorite things to teach in stats because I think it gives us a lot of interesting information. Today we are just learning, or in this lesson, we're just learning how to use the standard normal curve. And then in next time's lesson, well, 2 lessons, we're going to get down to how you can actually use the standard normal curve to solve problems, and that's when it gets interesting. So really important because we see it in more than just this unit. And 2, I personally love it because I think that it's interesting to find the probabilities and interesting to solve problems related to the standard normal curve. Okay, so beyond that intro, we have our curve. This all starts with the question, what if a data point lies 1.6 standard deviations above the mean? So let me tell you where this question comes from. So we have the normal curve. Notice that this set of notes is the normal curve, and our set of notes today is the standard normal curve. They're similar but different in a very important way. So a normal curve, you can use the empirical rule to find probabilities, percents, or areas. And the empirical rule says if you have an approximately normal distribution, 68% of your data will be within 1 standard deviation, 95 will be within 2, and 99.7 will be within 3. But this question that your notes begin with says, what if it's not 1, 2, or 3 standard deviations away? What if it's 1.6 standard deviations away? What if it's 2.78 standard deviations away? Because when we calculated z-score, look at how many different standard deviations we got. This is a negative 0.46 standard deviations below. We could not use the empirical rule to find the percent that is less than this z-score. We couldn't use it for the next problem, 1.63, or the next one, negative 0.85. In fact, if we look at all of these z-scores that we found, which tell us how far away a data value is in terms of standard deviations, if we look at all of the rest of them that we had in our notes, none of them are 1, 2, or 3 standard deviations away. So when we learn the normal curve, we get a lot of nice z-scores, I guess you would say. These questions ask things like what percent of response times is less than 15, but luckily 15 was only one standard deviation below the mean, so we were able to use the empirical rule. So moving on in this unit, from that, moving on from z-scores and the normal curve to this unit, the first thing that we did was transform data. And at this point, we're not really connecting those things. It seems like we're going between two completely different ideas. Last time we talked about transforming data. So what happens if we take an entire data set and add things or subtract things, multiply or divide? And then all of a sudden, now we're into this lesson that seems completely different, which is this thing called the standard normal curve. We will connect these in 2 lessons from now, but they are related. So we are pretty much going from the idea of the empirical rule and 1, 2, 3 standard deviations away to this newer problem or question. What if a data point lies 1.6 standard deviations above the mean? So remember, when we get a number like this, 1.6 standard deviations above the mean, that's a z-score. So underneath here, using the 68, 95, 99.7 rule is not very helpful in finding the proportion of observations for a given interval. The reason why it's not very helpful is because it is only 1, 2, and 3 sigma. So it only works for a z of 1, 2, or 3. So I'm actually going to write that down. And it may not make sense to you now, but by the end of the unit, it should make sense to you. Hopefully, it does make sense to some of you. Using the empirical rule is not very helpful because this is, or we should say, you can only use if z is plus or minus 1, plus or minus 2, plus or minus 3. So the only z-scores that we can use on a normal curve, So remember, let's point out the difference one more time. This is the standard normal. This is a normal curve. So empirical rule only works on a normal curve, and it only works if your z is 1, 2, or 3. So what's very helpful is that you can find the proportion or percent or area or probability, that all means the same thing, of observations for any interval. And when they say any interval, they mean any z-score by using the standard normal curve. So what makes the standard normal curve different from the normal curve for which we use the empirical rule? Well, the standard normal distribution, or the standard normal curve, is just the normal distribution, but it has a mean of 0 and a standard deviation of 1, always. N, 0, 1. It is always 0, 1. The standard normal curve always has a mean of 0 and a standard deviation of 1. Now, if we're going to be able to find the area, proportion, percent, probability of any z-score, that means we have a lot of different probabilities that we can find, because if you go back to our z-score notes, what you saw there, I think we did around 7 or 8 z-scores on those notes, and probably more throughout that unit. We've probably seen 20 or 30 different z-scores at this point. And you have to think about the fact that we normally write a z-score to the hundredths. So that means that you can have a z-score of 1.11, 1.12, 1.25. There are so many different z-scores that you can have, and that's where this normal table, this standard normal table, comes in. So all of these numbers inside of the table are areas, proportions, percents, probabilities. Those all mean the same thing in stats. The area to the left of the curve, the proportion to the left of the curve, the percent to the left of the curve, or the probability left of the curve. So all 4 of those words mean the same thing. Those proportions, percents, probabilities, areas are inside the table. Then, down the column and the top row, this tells you what your z-score is. This tells you your z-score. So down the row is your whole number and your tenths place. And then across the top is your hundredths place. So this is where we come to find all of those values. If you flip it over, you get all of your negative z-scores. Because remember, in your normal curve, you have 0 in the middle, and then positive standard deviations to the right, negative standard deviations to the left. So the standard normal table is a table of areas under the standard normal curve. The table entry for each value is the area to the left of z. It is always the area to the left of z. Couple things that I want to write down here or highlight. The first thing is this word areas. I'm just going to make a list. Areas is the same as percent, is the same as proportion, is the same as probability. That area under the curve can be referred to as these 4 things. So here it says areas, but it could have just as well been percent, proportion, probability. Okay, the other thing that I want to highlight is that your standard normal table tells you at the top that you're finding the area to the left. That's what this picture is trying to remind you of. The z-score is here, and what inside the table gives you is the area to the left of that z-score. Same thing if you look at the positive side. Whatever z you look up, it's the area to the left of z. So how do we use this table? Our first one says, find the area to the left of z equals 0.81. Okay, so what we need to do is mark on our standard normal curve. So the first thing that I'm going to do is list the parameters. N0, 1. Notice at the bottom of this curve, it is already labeled 0, 1, 2, 3, -1, -2, -3. Now we're going to plant a flag. Your flag can look like whatever you want it to. Mine's not very straight, oh well. And we are going to label this z equals, not negative, 0.81. Then we're supposed to shade in the area that we're finding. So they want to know the area to the left of this z value. So then on our standard normal table down the side, we are looking for 0.8. 0.8. So that's this row. Then you go over to the 0.01. So this is 0.81. This intersection here is the area. So this is the z-score of 0.81. So I will mark and say area equals 0.7910. One thing that I want to highlight here that was a common misconception, well, maybe not common, but I saw it more than once, is that some of you guys think that this normal curve stops at -3 and 3, or stops at 3 standard deviations and -3 standard deviations, and that's not the case. This normal curve can go on forever. There is no stopping point on this x-axis. What we know, though, is the percent of data that is past the 3rd standard deviation is very little. It is very unusual for your observations to be farther away than 3 standard deviations. It is not impossible. It is just unusual. Anything farther out than 3 standard deviations is an outlier, like determined by 1.5 times IQR outlier. So if it's more than 3 standard deviations away, it's an outlier, but it's not impossible. Remember, there's 0.15% of data that is more than 3 standard deviations away, and 0.15% of data that is less than 3, well, I shouldn't say less, more than -3 standard deviations away. So if you have a sample size of 10, none of your data values are probably bigger than 3 standard deviations away. But if you have a sample size of 10,000, that means that 100 and up to 100, I'm lying, let me double check. Let me double check. Up to 15 of those observations are farther away than 3 standard deviations. So all of that to say, this does not stop at +3 and -3. Okay, the last thing that we need to do is write the correct notation. So we're going to write capital P. Because remember, area, percent, probability, proportion are all the same. So we're going to use capital P of Z less than 0.81 is equal to 0.7910. Make sure that you get your equal sign here. So at this point, all of this is required. You have your parameters, your flag, your area shaded, your area labeled, your statement that is your answer. That's 1, 2, 3, 4, 5, 6 things that you need to include to do one of these problems thoroughly. Okay, the next problem says find the area to the right of z equals 0.81. So on this standard normal curve, I label the parameters. I plant my flag again. I label Z again, but this time I shade in the area to the right of the flag. Well, based off of the last problem, I know that this area that I did not shade in is 7910. Well, underneath this curve is 100% of the data. So if we want to figure out what's to the right, given we know what's to the left, you calculate that by subtracting it from 1. So we would say P of Z greater than 0.8, sorry, 0.81, is equal to 1 minus 0.7910. If we plug that into our calculator, we get that the area is 0.2090. So I can now label the area that I shaded. So now I'm going to zoom out and I'm going to try to address some things that I think may be a little bit unclear. First, this little snippet, this picture is a little snippet from this table. So if we were using this table, I would go down to z equals 0.8, and then I would go over to 1, and notice that the probability is the same, 7910. These inequality symbols, you don't have to worry about the less than or equal to situation for now. Until we get into real world problems, you can just use a less than and a greater than. I'm not using a less than or equal to because this says it's the area to the left, which to me means it doesn't include 0.81. It's the area to the left of 0.81. I don't think that there is a real distinction. I think that in stats, either one is fine. I'm just explaining to you why I'm choosing not to use the less than or equals to. I think that that's all of the things that I wanted to make sure that I highlighted. The area under any normal curve. So this area under a normal curve. Area equals 1 or 100%. So that's why down here I did 1 minus 0.7910, because the area is 1. If you wanted to convert this to percent, you would say 20.90% of the data is greater than 0.81 standard deviations. This is 79.10 So 79% of the data is less than 81 standard deviations. You do not have to write these percents. I'm just showing you what these percents would equal. Maybe I should have written it over here. That might look better. This is not required on today's practice problems. I am just writing that in so that you can make the appropriate connections. Okay, so on our next page, we are going through a bunch of different areas that we may be asked to find. And this is where we're going to start using our purple normal table paper or laminated paper. Okay, so now we're on the back side, and we are going to look at different probabilities that we can be asked for. So this says use a z-table to find the following areas. And I have left blanks for us to write in that these have different names. They mean the same. They're just different. So one is percent. One is proportion. One is probability. I want you guys to get used to seeing it referred to all four things. Referred to as all four things. Because some of your real world problems are going to ask you to find the probability, and then other real world problems are going to ask you to find the percent. So we got to get used to knowing that area is the same as percent, proportion, or probability. Okay, on number one, they want us to find z less than 0.54. First thing we do is write our parameters. Then I'm going to label the x-axis. Then I plant my flag at 0.54 and I label it. Man, that flag is not awesome, family. Let's try again. Your flags can look like whatever you want them to look like. I'll draw some different ones on the next few. So this is z equals 0.54. You shade in the area that you're looking for. Now we go to our z-table. You can split this if you need to. So down the column, we're looking for 0.5. And then across, we go to 4. So 0, 1, 2, 3, 4. So I am getting 0.7054. So P of Z less than 0.54 is equal to 0.7054, which would convert to or equal to 70.54%. Okay, next up is a z of negative 1.12. So I list the parameters for my curve. Guess I can get it a little bit closer than that. I plant my flag. Oh, just kidding. We need to label the x-axis. So 0 in the middle, 1, 2, 3, -1, -2, -3. Now we can plant our flag at negative 1.12. Oh, I was going to do some different ones. So you could just do a triangle flag if you wanted to. Label it. Then shade in the area that you are finding. And yes, the shading in is required. I don't typically make you guys do things unless it's necessary. So this time we're on the negative side of our z table, our standard normal table. We're going to go to negative 1.1, then over to 2. So we're going down to negative 1.1, and then we're going to the right, so 0, 1, 2. So this area is 13, 14. But we want this area. So that means the area to the right of negative 1.12 is equal to 1 minus the area that was to the left. That ends up being 0.8686. So I write that down on in my answer area, and I labeled it on my curve. Okay, next up, they want us to find the area that is between 0.49 and 1.82. So I'm going to draw this on a separate piece of paper first. So we have our standard normal curve, 0, 1, 2, 3. And they are asking us to find the area between a z of 0.49 and a z of 182. So they are asking us to find this area. Okay, well, in order to do that, we have to look at both of these z values that they gave us. So they give us a z value at about 0.5, and our table is going to give us this area. Then they give us another boundary of 1.82, and that's going to give us this area. But remember, all we really want is, so watch me do this if you haven't been watching. When we find these areas on the z table, we're going to end up getting the z for this lower bound, and that is shown here. And then we're going to get the area for this upper bound, and that is shown here. Now this is the part that I want you to watch to make sure we're all on the same page. They only want this area that I am highlighting in yellow. So the easiest way to get this area is to take this for the upper bound and subtract the area for the lower bound. When we do that, instead of getting the area to the left, we get this area. So you take the entire area to the left of the upper bound and then cut off the area that's below the lower bound. So hopefully that's making a little bit of sense. If you want just this area in yellow, you take the area of the upper bound and you subtract off or take off the area of the lower bound. So now let's see what that looks like in terms of actual z-scores in the z-table. Okay, so we label our thing. So the first thing I'm going to do is label that the lower bound is 0.49 and the upper bound is 1.82. Then I'm going to write down that any problem that is a sandwich like this is going to be the area of your upper bound subtract the area of your lower bound. Okay, now I'm going to label my curve with its parameters and then label its x-axis. Okay, next up, I'm going to plant my flags. So I actually need to move this over. Sorry about that, guys. Because I need a flag at z equals 0.49. And I need a flag at z equals 182. So just like I said I would, I'm just drawing different kinds of flags. I mostly use this one. You could use a triangle, you can use this. Okay, so the first thing that we're going to find is the area of the upper bound, so I'm going to shade that in. And I am going to write the area right underneath my flag. So I'm going to go back to my positive side. I go down to 1/8 and over to 0, 1, 2. So I'm getting 9,656. So the area of the upper bound is 9,656. Now to get the area that we want, we're going to have to take off this area to the left of our lower bound. So the area to the left of 0.49, so on this one, we go down to 0.4, and then all the way to the end of our table. So I'm getting 6,879. So to show what we did mathematically, the area between 0.49 and 182 is equal to 0.9656 subtract 0.6879. I'm using this formula right here. Area of the upper bound, area of the lower bound. So if you plug that into your calculator, you get that that area is 0.2777. Area is 0.2777. Sorry, I'm just fixing my shading because I don't like it. So some of these take a little bit longer, obviously, than others. Okay. Next one is number 4, within 1.5 standard deviations of the mean. So we can start by listing the parameters for the standard normal curve and then labeling the x-axis. So n is 0, 1, x-axis is 0, 1, 2, 3, -1, -2, -3. Okay, well, within 1.5 standard deviations, well, that means that our upper bound is z equals 1.5, and our lower bound is z equals -1.5. Because remember, our number of standard deviations is just our z-score. So what we're looking for is this area between the two. Okay, so we need to find the area for our upper bound, and we need to find the area for our lower bound. Lower bound, we're going to negative 1.50, because there's nothing after the 5. So negative 1.50 gives us 0.0668. The area for the upper bound is 0.9332. So the area that is within 1.5 standard deviations of the mean, well, I know it's going to be greater than 68, because 68 is 1 standard deviation away. So P of negative 1.5 less than Z less than 1.5 is 0.9332 minus 0.0668. We do get an area bigger than 68%. It is 0.8664. So 86.64%. Okay, we have one other type of problem that you will see when working with standard normal curves. So we have the area to the left. We have the area to the right. We have the area between. We have the area within. These two are the same thing, just different words or different ways of being asked. Then the last one is number 5. The last kind of way that we can be asked is number 5. So we write our parameter. We label our x-axis. And we plant our flags. So we want to find the area that is less than negative 1.25. And greater than Z of 2. Okay, well, what the shading looks like for that then is area to the left of our lower bound, area to the right of our upper bound. So we'll take this one step at a time. So the percent that is less than the lower bound. So we are going to go to the negative side, down to 1.2, and over to 5, which gives me 1056. So this area is 0.1056. Okay, well now we need to find the area to the right of 2. Well, that's going to be 1 minus the area to the left. So we go to 2.00 on the positive side, and that gives you 0.9772, which gives us an area of 0.0228 to the right of z equals 2. So now we just need to add those two. The correct symbols for this is P of z less than negative 1.25 intersection or and z greater than 2. This is the mathematical symbol for and. It's also referred to as an intersection. 0.1056 plus 0.0228 equals 0.1284. The area that is less than negative 125 and greater than 2 is 0.1284. So we have one last between normal curve. You should pause the video now. I'm going to pause my video. I'm going to fill it out and then let's check in. So you pause, I pause, and then we're going to check in. Okay, so I am getting 7621. Lower bound is negative 2.05. Upper bound is 0.78. Notice that I only shaded in what they wanted. Up here, I shaded in both to kind of illustrate what was happening. Same here. But now on this one, I'm only going to shade in what they're actually asking for. I ended up getting 0.7621. I could be wrong on some of these. You guys know that. I make mistakes all the time. So if you're getting something different and you're feeling really confident about it, I probably just made some silly mistake. So leading into your check for understanding, just keep that in mind when we check answers for this. I gave you the normal curve for the first 5. You need to draw the normal curve for the last 5. And you need to go through and do all of the things that we did on this page. Meaning you need to list your parameters, you need to shade in, plant your flags, make your answer statement. Everything that we did here, you now need to do here. So you're going to pause. In fact, you might just want to leave this because mine took me like a half hour. And when you're ready, come back and check your answers on this check for understanding. So pause. Okay, you're back now? Okay. So I'll just go one by one. For number 1, I got 9978. I did not list the parameters for my curve. I probably didn't on any of these. Number 2, 0.0069. I don't know why I didn't label the area there or the area here. So come on, teacher. This is 9978. This is 0069. This is 9931. Number 3, I got 9515. I think I said 5 and I meant 3, sorry. Number 4, I got 1798. Notice that I only shaded in the desired area. Okay, number 5, I got 0.0239. 6, 0.2410. 7, I got 0.3264. 8, how's the drawing your curves going? Because now you're in the portion where you draw your curves. 8 is 0.9726. 9 is 0.7621. 10 is 0.7823. So this worksheet was a doozy for me. It took me a really long time. So hopefully it didn't take you quite as long as it took me. Okay, so this is how we use our standard normal curve. I know that this number of curves seems extreme, but you will thank me for it when you take your AP exam and you know how to draw these curves in your sleep. So this is how we use our standard normal curve. So the next lesson is how we go backward. Today I gave you a z-score, you gave me an area. The next thing that you do is I give you an area, you give me a z-score. Okay, love you guys.